In this lesson, we want to look at a very specific, unique scenario that comes up when you multiply a binomial times itself. So, we're going to look at an example here of x plus 3 squared. Now, what some people would probably treat this as is thinking that this is just x squared plus 9. But is it x squared plus 9? Well, we have to think about what exponent notation truly means. Exponent notation means repeated multiplication of the base times itself that many times. So when we see this, we need to think of it as being x plus 3 times x plus 3. Now, as soon as we see a binomial times a binomial, we learned in the previous lesson that this means we need to enact the principles of FOIL to expand it and to simplify it. So if we multiply the first terms times each other, we get x squared. If we multiply the outside terms times each other, we get 3x. And because of the symmetry of this, we also notice that when we multiply the inside terms together, we also get 3x. Isn't that interesting that they're both the same? But it makes sense because, again, of the symmetry here. And then finally, 3 times 3 would be 9. Let's collect these like terms to see that, in fact, the solution is x squared plus 6x plus 9. Now, do you think that matches what we had up above at the beginning of the lesson? Well, it doesn't. It doesn't match because it's missing this middle term. So the biggest thing I want you to realize is that when you see this, it doesn't mean square the x and square the 3. It actually means x plus 3 times x plus 3, which has a very different outcome than if you just square the individual terms. Let's explore this again. Let's look at 2x plus 6 quantity squared. And again, we see that we go, that actually means 2x plus 6 times 2x plus 6. And then we see a FOIL opportunity here because of the two binomials being multiplied by each other. So, let's multiply the firsts together. We get 4x squared. Let's multiply the outsides and the insides by each other. Again, you're going to notice that they end up being exactly the same. And then if we multiply the lasts together, we get 36. We see that these inside terms are like terms, so we can simplify them into being 24x's in the middle between 4x squared and 36. Let's try this again. Let's look at, instead of a binomial where both terms are positive, where the second one is negative. How does this change things? Well, again, as soon as you see an exponent, you know that it means repeated multiplication of the base. Looks like another FOIL opportunity. So firsts are x squared, outsides and insides are both negative 4x. Maybe at this point, you could actually recognize you could add those together and get negative 8x right off the bat. Negative 4x and another negative 4x would be negative 8x. And then negative 4 times negative 4 would be 16. And then you could get to this final answer one step quicker if you recognize that a binomial times itself allows for you to have identical middle terms that can come together to make the middle term at the end. All right, we want to look for some patterns after we try one more example. Let's do 5x minus 2y quantity squared. And again, you see this and you realize that means 5x minus 2y times itself, so that there are two of them, 1, 2. Our firsts give us 25x squared. Our outsides give us negative 10xy. So do the insides, negative 10xy. So what if I have two negative 10xy's? That means I would have negative 20xy's. And then lastly, negative 2y times negative 2y would be positive 4y squared. All right, we want to look for some trends here. Okay, so the binomial is what we see in the original question. That's this one right here. And the trinomial answer that we get is what's in the pink up there. So I'll continue with pink down here. Here's the trinomial answer. Trinomial answer. Trinomial answer. Isn't it interesting that every time we multiply a binomial by itself, we always get a trinomial answer? Okay? So how is the first term in each of these answers? I'll highlight it for you. Here it is. Here's the first term. Here's the first term. First and first. How is it related to the first term in the binomial? This one, and this one, and this one, and this one. Well, because it results from multiplying the firsts together, it is the square of the first term in the binomial. Okay? So this is the square of the first term in the binomial. I'm going to skip and let's go to the last terms. So let's look at the last terms in the examples. There it is. There it is. I should have included the plus there. Hang on. There it is. There it is. Isn't it interesting that they're all positive? Well, why would it be true that they would always end up being positive no matter what? Well, let's look at how they are related to the last term in the binomials that they came from. Here they are. Notice that the last term in these first two binomials is positive, but the last term in these two is negative. Well, why is the answer always positive? Well, because again, this comes from squaring that last term. It is the square of the last term in the binomial. And regardless of whether a term is positive or negative, when you square it, its answer is always positive. So it's not surprising to always see a positive at the end. All right, the final pattern we want to look for here is what about the middle terms? So let's highlight them. Negative 8x here, positive 24, negative 20, and positive 6. And let's compare them to the original binomial. What do we notice as a pattern? Well, this middle term comes from multiplying the first term and the second term in the binomial together and doubling them. So think about it. Negative 4 times x would be negative 4x. Double it would be negative 8x. 6 times 2x would be 12x. Double it would give it 24. So why double? Well, again, that comes from the FOIL patterns we looked at. It's double because it results from the outsides and the insides being multiplied together and being perfectly symmetrical. So 2 of these terms results in the doubling of the answer. So there's all kinds of cool patterns in this. So what we do is we call this scenario when you multiply a binomial times itself a perfect square binomial. Because what it does is it gives us something called a perfect square trinomial answer. Perfect square trinomial because this has a square root, and this has a square root, and this is connected through the roots of both of these. Okay? We need to hang on to that term because we're going to come back to it in lesson 5.6. Okay? So perfect square trinomial is always the result of a binomial times itself. I'll say that one more time. A perfect square trinomial is always the result of a binomial squared or a binomial times itself. Okay, in the next video, we'll look at another subset of binomials times binomials. that yields a neat pattern.